Cool.
You guys see the video?
Yep.
Read the paper?
I couldn't
I saw the
quite
video.
find the paper. Did you?
Let me just name the same thing. You'll search. So like
Oh.
this. So Alex Damore, you can message him in the forum. He logs in sometimes. He's so he works at Google in Cambridge, Mass, and his background's largely in causal inference, particularly from that kind of statistical side of it. He's the one, like, so David Bly had this paper called The Blessings of Multiple Causes, where he kind of supposed where that's, if you could say, take a, you have a relationship between X and Y, a cause and effect, but the cause is multidimensional, and if there's a confounder, then you can kind of infer like a low dimensional latent variable and effectively adjust for that latent variable as a proxy for the confounder. And which seemed cool, seemed like causal effects for free just because in high dimensional settings. But Alex Damore, like with this very trivial example, like multivariate Gaussian, just proved that it doesn't work. Which is, it was great because, like, David Bly is kind of a giant, and it was just like, and he wrote this big, and David Bly wrote this big long paper with a whole bunch of different arguments backing it up, and then this guy writes like basically like a 3-page rebuttal and gets it submitted into JSM, and which is a statistical journal, and but it's the main statistical conference, so it's not a machine learning journal. It's like a big. So it kind of looks like a statistician, like, this is bullshit. What are you doing? Anyway, it was kind of like an upset in the stats world. But
there's also a controversy with Judea Pearl, between Judea Pearl and
this guy. So Judea Pearl went on to, like, after this guy put out this paper and called the problem under specification. So you saw the video, and basically the idea is like, something that I think all of us kind of already intuitively knew, which is that all of the hyperparameters, all the little tiny decisions that go into the machine learning pipeline, that training and testing validation workflow is not sufficient to ameliorate the impacts of those choices on the output, and so that so he just basically wrote the experiments that showed that, like, all right, fine, we're gonna have these different. We're just going to have the same. We're going to have various. We're going to take a model, just kind of have some slightly different settings for the hyperparameters, but then do training, do cross validation, do optimize for predictive accuracy, and validate on a test set, and then show that on kind of the held out data it's supposed to generalize to, you get wildly different results.
Did I miss something? Does that go beyond that? Because that's the first thing I learned in Andrew Ng's course like a decade ago. That's obvious. Like, is there anything more to it? Because did you need to do these experiments? I thought it was pretty obvious that it wasn't going to work. It's obviously assuming that your test set is the same distribution as your validation. Once you change that, then obviously it's not going to work. Why do you expect it to work, I guess?
I mean, to be clear, so wait, what is it that you say it again?
So I guess I didn't find anything that I hadn't seen like 15 years ago in a basic machine learning 100. I would say the experiments were very predictable. You didn't need to do them. That's my point. Like the experiment, like with the camera, if you use a different camera, your inference isn't going to work. Of course not, because your distributions are different now. So if you want it to work, you have to train on. So I think it's always, we always assume that the test distribution in the wild is going to be the same as your validation. And if it's not going to work. I think that's common knowledge, isn't it? Like, did it go beyond that?
Yeah, so I think so you assume that the model that you learn is going to underperform slightly on a different set of data that's slightly, you added some noise to it or something like that, or the colors were different. You assume it's going to underperform relative to the test set. But I think what they showed was that the amount of that there was a large variation in performance depending on based on hyperparameters that were not supposed to have a huge impact, right? Like for example, the seed of your algorithm the random seed of your algorithm shouldn't have a huge like changing the random seed if it's having, like if this seed has a different impact on the new data and that seed has a different impact on the new data, then it.
Yeah, but I mean, once you call it new data, new distribution, all bets are off. I think anything could happen, right? I mean, if your test distribution is almost the same as your training distribution, then the hyperparameter shouldn't have a large effect. That I accept, but I don't know why this was surprising. I guess I must be missing something.
I guess I have a comment that it feels like before, when we built machine learning models, it was done in a smaller domain, and we weren't applying them as broadly. And so there were always domain experts around kind of looking at it. And it seems like things have switched, that models are being applied far more broadly, and that data drift now has just become like, we understand that it's there in a way that I think it was always understood that there was possibility for that, but because of the way the models are being deployed and used, it's just become so much bigger of an issue.
Okay, fair enough.
I can say what surprised me about it, like I know that, so seeing underperformance once you kind of change the data, change the generating, the data generating function away from what it was in the training data, seeing a little bit of like underperformance. Like I grew up learning statistics, and so it was just like, yeah, you saw it there, like training data, you had the logistic regression had this fit, and then the had this predictive accuracy, but then the test data had less predictive accuracy, but then you kind of permute the data a little bit, and then you had even lower accuracy. I expected a dip in accuracy if you kind of change, the contrast in computer vision, for example, for like tumor recognition. But I didn't expect wildly different results based on hyperparameters that shouldn't matter. Hyperparameters that I assume, like whose impact on the problem, on the fit, on the predictive accuracy, I assumed would have been treated by the test validation workflow. In other words, that like, if I can take two models of the same architecture and have different hyperparameter settings, but then tune them so that they have the same predictive accuracy on held out test data, that I would have assumed before seeing this paper that if you applied them to different, like so slightly altered distribution, that's, whatever differences in predictive accuracy they have, they would have been trivial. There would have been statistically insignificant differences.
But usually the test data, you just pick randomly from your training data. So it's the same distribution, no? So it's not slightly different. Your test data is not actually test data. It's the same data. You just
so I guess we need a new name for that third. So the third data set is like drifted data. Can we just call it that? So we have the training.
But do we have that? I've never had the access to something like that.
Well, just like, data that comes later on, that's in production data. So we say like training data, test data, I was going to call it data, drifted data.
Okay,
and so I would have assumed that the whole point of like of a cross-validated workflow, right? Just that you hold out some test data and then you kind of optimize the algorithm so that you're training your parameters on training, and then you evaluate it on test. And that, so if you had two models, same architecture, different hyperparameter settings, but you both optimize them using a cross-validated workflow so that the whatever little weird things the hyperparameters do to cause you to overfit, you've adjusted for that using test data, using cross-validation on test data. And so having solved that, I would have imagined that once you now take these two models and use them to predict on the drifted data, any differences, they would both underperform relative to test, obviously. But I wouldn't have expected that different hyperparameters would have led to different, like dramatically different outcomes on the drifted data. That's kind of a surprise to me. I would have expected there to be difference because of randomness, but not statistically, not in a statistically significant way.
Yeah, I guess we kind of know that these neural networks like take shortcuts, right? Like if you give them labeled data, if there's any way to cheat and it's easier, they will do it. So if you leave a whole bunch of things underspecified, of course, they're going to exploit it to get best in performance. But I guess there was only one slide he talked about solutions to this, which was, I don't know, we should come together and fix this kind of thing. There was no solution. Is there a solution from causality literature, or because it looks like you need to know what you're adjusting for before you adjust it. But if you know it, you might as well include all that into your training data and then it'll fix it.
I mean, I think the point of this paper is like, so, I mean, the other thing that we're taking for granted is like having kind of been familiarized with the causal modeling literature and causal inference literature. We know, for example, some theoretical ideas like equivalence classes, this and that. Alex Demore is trying to communicate these ideas to basically the Google organization, and so people who are all kind of very much into deep learning and are trying to get and they productionize deep learning and expect it to work, and so they needed to show across a wide variety of applications with like cutting edge algorithms, like, okay, we're going to like apply it with large data sets using compute, like using Google level compute, and they spend money on this paper. Like if I just showed it to you, I just showed it to a Google employee on one example with like a neural nets that I trained on 10,000 examples on my laptop, they're just going to say, well, that's because your data is too small, or because you're not using all the right resources, or you're not using dropout, or you're not using this. And so like they had to kind of show. They had to basically get rid of all the yes, but objections. I mean, you're right. At the end of it, it's kind of like, you kind of walk away. Well, I guess machine learning's fucked. Kind of like nothing.
There was one point he made that I thought it was interesting. That when I think somebody asked a question about ensembling. So if you actually use a bunch of ensembles of the model and you're still underspecified, the average of those does not get you the right results either. Like, so if you're not actually training in the right distribution, ensembling doesn't help you, which is sort of obvious, but I hadn't thought of it. Actually makes sense that you can't sort of work your way through these problems by just averaging more random models.
Mm.
Yeah, that was a really good point, actually.
Yeah, that was a surprise to me as well. I thought at least you could reduce kind of error doing that.
There was this paper, I don't know if you read this here, by Leon Batu about using causality. And I think he got to this point, like the example they use, if you have like two data sets that are come from different distributions, he was saying that most people, they mix the data and then they train a model to be insensitive. And he was saying you should not do that. You should exploit the fact that there are different distributions and use it to make the model more robust. So that was his whole, I mean, he tried it on very small toy data sets. I think if there were some practical issues from scaling it up, I mean, beyond the fact that it's really hard to get the data from different distributions, but that seemed to be going on the right path. Like it was using causality and all that. I'll try to find it. I can't remember what it was called. Something about risk minimization.
Empirical minimization.
Leon Batu.
Yeah, he's at Facebook, I guess.
Jeremy, did you have any insights? Did you watch the video?
I didn't get a chance to watch the video, but I am familiar with this paper, and so so is it which paper were you referring to for Leon Batu?
I think it's called Invariant Risk Minimization.
So there's a linear unit test for invariance discovery. You're saying something else.
I shared the link.
Oh, cool. Oh, I see it now.
Hmm. Yeah, I mean, it's
Cool.
Rose brought up the issue with Pearl. Like, so Pearl criticized the paper on Twitter because
John Urbanic kind of put Pearl back in his place. He says, "Did you see that? Did you see his response to that?"
No, I mean, it was annoying because if you read it, if you knew his background, you read the paper, it's kind of like, all right, well, this guy has strong causal inference fundamentals. He's not trying to sell a bunch of machine learning engineers and why you need to be using causal models. He's telling them, he's taking their existing workflow, so and running experiments on it and showing why it's why things do not generalize, and showing it consistently across different domains of different with cutting edge architectures, and then and it's showing and then kind of the final argument was that I think the analogy of putting blocks into the thing was good, because he's saying that if you want somebody to put a block, but you don't want the algorithm to put a circle block into a square hole, then you have to write some kind of constraint on the algorithm that says you can't do that. And of course, that begs the question of how would you do that? And of course, if you have a black box model, that's very difficult. Although in theory, you could maybe design a loss function that somehow targeted that. So I mean, I think thing about causal modeling is that it's a model-based workflow. And you could solve the problems of causal modeling with constraints on optimization or constraints on a loss function. It's just hard, but it's possible. You got to, it's like you could figure out a way. You could figure out a way to do it. So I don't think anybody wants to close the door on those things. But yeah, it's like he didn't explicitly say that you need a causal model, because that's solutioning, right? It's when I was like in engineering, do you articulate the problem before you come up with solutions? Judeo-Pearl, of course, was just like, well, I already have the solution. Machine learning's stupid because it's the do calculus. But yeah, that was kind of the lame thing for him to do. What was the response, Jeremy? I didn't see it actually.
Yeah, I'm trying to pull it up right now. That's not it.
I was also a little surprised he didn't make explicit the links to data augmentation. Obviously, one way to approach it is looking at this from augmentation, right? Like you're obviously not augmenting your training data in ways that will mitigate some of these problems. Because a lot of those variations were just like augmentations, like adding Gaussian noise. You could do that during training. You don't need to hope for the model to work, right?
I found the Twitter thread, I think. Sorry, I didn't mean to interrupt you.
No, go ahead. Yeah, I'm done.
Okay. So he says, basically, I respect Judeo-Pearl's thought leadership. This idea logging is painful to watch. Concerned with communication strategies, one might consider more tact than comparing 40 researchers to a pre-algebra child or calling their work hilarious/grotesque. Toy examples that Pearl suggests are extremely useful, but there's also a place and need for the kind of work Alex Damour's team is doing to reveal how fragile the models people are actually deploying are. The paper is not trying to solve a bug. It's an empirical survey of how lack of identifiability is impacting real-world problems. Damour and several other co-authors are students of the causal hierarchy. Most ML teams are not. We need to reckon with the fact that ML researchers are tackling big problems and seem to be finding success for some definition of success. Toy examples do not enlighten someone who thinks the solution is just more data. My read of Underspecification presents challenges is like a gateway drug to exploring causality. Colleagues and professors told me causality was too hard to use in practice, so I shied away. I only started exploring more deeply after I started interrogating my models. As I interrogated these models, I recognized that aspects of concept drift, underspecification, and other problems were often issues with unobserved confounding, identifiability, and transportability. But in my day-to-day, I'm expected to help produce deployable models. I studied the causal hierarchy and started adopting an iterative model building / checking validation workflow like stats modeling's Betancourt or Gelman's Bayesian workflow to try and incorporate some causal thinking. Papers like this play an important role in getting ML practitioners thinking about confounding, transportability, and counterfactual inference. Leaders like Judah Pearl and Elias Barenboim should support it and recognize the opportunity to bring more people into the causal inference fold.
Very articulate, makes perfect sense.
Yeah. So then after that, Judah Pearl's like, you're right.
Oh, he did?
Yeah.
Oh, I thought he didn't ever do that.
No, he does that all the time. He's very quick to admit when he's wrong.
So
Unless it has to do with politics, and then he's never he never. Well, actually, I actually did. I sent him a message about his politics that he actually respected, which is kind of cool.
You really you went toe to toe with him on like Israeli politics?
Yeah, I did, and he was actually open to it, which is like surprising, right? But he really did. Let's see if I can find that. Oh, that's a whole other issue. I'll let you guys continue the conversation. I'll find that tweet. I'll send it out.
So Robert, on the question, so you've been discussing in a series of posts the paper that
Just link the original.
yeah, the causality paper that Bengio kind of chimed in on, and it kind of pointed at some fundamental problems around the belief system supporting IID data. Do you want to comment? Like, does this relate back to what that paper talks about, or is that like the identifiability stuff? And is there crossover between what was discussed in that paper and this one?
I mean, yeah. So I think earlier you mentioned like Bateau's paper about not mixing distributions. So, you know, so like what? So that was a paper by Shokoff and Yasha Bengio and some others who were arguing that you know, a lot of the so a lot of the machine learning kind of operates on this assumption of IID, like the algorithms essentially assume that, and that's and characterizing like basically causal identification issues, or insofar as they affect the robustness of prediction, as a problem of assuming IID is there when you don't have it. And so that's analogous to Bateau's, or I mean, it's the same idea of Bateau's kind of idea of that you shouldn't mix up distributions, because mixing up distributions is just trying to artificially engineer IID. And, you know, so I'm not sure, like with this paper, they say like the paper is IID. Like I'm not sure what he means by, this might be a good thing to clarify. So in the beginning of the talk, he says, yeah, okay, under specification, an ML pipeline is underspecified if it can handle multiple distinct predictors that achieve equivalently strong IID generalization performance. And so IID generalization performance seems to be performance in validating on training on the training data and validating, training and validating on training data, and then kind of testing on test data. Like that's so
IID, let's just drill into this a little bit. So IID is assumed to be naive Bayes, right? So there's no confounders, there's no kind of causal structure in the data generating process that's generating IID process, because otherwise what we should be doing is decomposing the data that we're seeing into the discrete causes that are conditionally independent. Is that?
It doesn't, so IID is a assumption about the joint probability distribution of the data. It's not an assumption about, it doesn't say anything about the causal processes that.
So this is where I get confused, because to me, how can you do that? Like, is that even legitimate to do that, to actually take like confounded data and then somehow draw inference from it without knowing what the confounding is? Or maybe that's the wrong question. Maybe I'm just framing this very poorly. I don't know. I don't have good thing.
Well, it's interesting because it's a difficult, because the semantics are from two different languages, right? So IID is from the language of probability and statistics, and confounding is from the language of causality. And and so the question is, are there cases when if there is confounding, can it cause the data to not be IID? I suppose the answer is, well, yeah, I guess by definition, confounding means the data is not ID because for different values of the confounder. So let's say you have 100 data points and you have a confounding variable with 3 levels, and maybe like 33 points are from level 1 and 33 points are from level 2 and 33 points are from confounder at level, 34 points are confounder at level 3. And so those are all kind of, so you have data, 33 points that have the probability of X given confounder equals 1, and then 33 points probability of X given confounder equals 2, etc. And so those by definition would be non-IID data. So it's like, what they're saying is, they're trying to, when people talk about this, they're saying like, they don't want to bring in causal semantics. They want to say like, because of reasons, the data is not IID, but your algorithm assumes it is. And especially now, so if, for example, there is some level of the confounder that's not observed in the training data, then that's why this is going to be a problem. And so,
so if you have a collider, for example, and there's no actual situation where the collider triggers, and then in the real world it does, your model's not going to have any predictive accuracy at all.
Yeah. So collider is one example. Maybe even just the simple kind of backdoor confounder, like,
sure.
Let's say that I have 2 data sets, one where the confounder value is A and one where the confounder value is B. Then the traditional kind of way of kind of addressing this is by mixing the data so that it's like I'm marginalizing over the confounder for the values of the confounder that I have, and assuming that that's kind of marginally IID. But the problem comes from when you encounter values of the confounder in production that were not mixed up in the data. So the example I wrote about in this blog post was MNIST. So MNIST was comprised of NIST data, and NIST data had several populations that were labeled. One was from Census Bureau, characters written by Census Bureau officials, and the other by high school students. And so Jan LeCun and his group basically solved this by mixing both data sets together.
Okay, and is there a strong kind of argument to validate the assumption that IID is even a thing? I mean, or is IID just a convenience that gets you to better than random, but it really doesn't take you much further than that? Like if we could develop a test.
IID is a theoretical idea that we can define in probability theory. The question is, and when we assume a data set is IID, we're assuming that the underlying joint distribution of the data is IID, and that's an assumption. The question is that assumption ever one that's like, is it too strong an assumption to be used in reality? Is, I think, your question.
Well, I think the way I would think about it is not that joint distributions can be IID, but you can sample from a joint distribution in an IID way, right? Yeah. So I could have a joint distribution with an SC. I could have an SCM that generates, that's associated with an SCM that generates a joint distribution, right? And the question is, how do I sample from that joint distribution? If I sample from it in an IID way, then I will have an unbiased estimate of the joint distribution, and my training set, as long as my training set and my test set were sampled in the same way, in this IID way from that joint distribution, my training set, my test set should do just fine.
Yeah, so experiment, for example, you could like take replicates from a controlled experiment and IID assumption there because you're controlling the data learning process. So I guess the question is like, with the kind of observational data that we see in practical settings, it doesn't make sense to assume that the sampling, to assume that this process is like IID sampled data. And I think it depends on the domain. I mean,
but I mean, the whole point with Alex Damore was, I thought the whole point with Alex Damore, and please correct me if I'm wrong, because is that the machine learning models were trained and tested in the IID setting, right?
I think I quote unquote IID evaluations, like on this slide here, is just a cross-validated workflow like we see here. So we got some training domain, get some data, we're doing some training or some validation, got some test data. I mean, there's different ways of going through this whole
thing.
And I think like just this best practice here, he's calling IID evaluations.
But he's saying actually, if there's more than one machine learning algorithm that can if there's more than one predictor that can achieve equivalently strong IID generalization performance, then it's underspecified. So he's saying here that I could have two different parameter settings that result in the same observational, that, you know, if you were to sample from them, it would produce the same observational distribution. And that's a problem, right? Because, you know, that means that there's non-identification of parameters.
That gets back to what I was trying to get at, Jeremy. So thank you. Yeah, very good. Yeah. How can you have a system that is not underspecified if you don't have a full causal model? There you go. I'll ask that question. Like, I think that there's a kind of a corollary here, which is a model that does not have I know there are special names for all these things. I can't remember all the millions of names of things, but basically, if you have a model that is parameter complete and is correctly organized, then that's not underspecified because you have sufficiency, right? You have everything that you need to make good predictions. But in all other situations, correct me if I'm wrong, it's underspecified.
So here's a counterexample. Let's suppose, so using causal ideas, let's suppose that I have a variable y, and I have and I have, according to, so I have some ground truth causal graph, which gives me the Markov blanket for using a Markov blanket for y, right?
Right. And
so I train, and my task is prediction. All I want to do is predict y.
Mm-hmm.
So I use the Markov blanket for prediction as predictors in a black box model. So that model will, by definition, will be the best predictive model. I mean, assuming that I have infinite data and I have kind of learning theory at my side, I can use a neural net. Then that model will be the best predictive model I can have for that predictor. And the only thing that I've used, and I haven't, and say all I know is that these things are members of the Markov blanket. I don't know that I don't know what the causal structure is, or I know causality insofar as I know that they're a Markov blanket, but I know nothing beyond that. So the parents and their children or their spouses, right? Like in a Markov blanket, and so like. But I don't know which is a parent and which is a child and which is a spouse.
Mm-hmm.
So I don't have the full causal structure there, but that would be a theoretically perfect predictive model.
I was asking on the chat, but so one of the examples you showed that I found interesting was those ophthalmology, like different cameras, right? Like you train in one camera and then it doesn't generalize to other cameras, but you don't train radiologists by training them over a billion cameras, right? You train them with one, and somehow they just as easily, probably with a couple of examples, generalize to a new camera. So there's obviously ways of generalizing beyond the training data. So the question is, what is it? What is it? I don't know if you need causality like directly, but there is something. Obviously, there is information about in just the one data set. Obviously, humans come in with a lot of other information. The question is what?
I think that there are also generalizations though that humans miss, or sorry, that we generalize in ways that are also incorrect, right? So
Sure.
the camera is one way maybe the machine would, but through training, we're looking for something in particular, right? And so there are advantages to both, right? Maybe machines can catch something that people can't catch, and people can catch things that machines can't catch. Right,
Well,
it's understanding the limitations to both, right? That's kind of why it's valuable for us to not think about it in terms of black box, because what are you using to make that decision? Because if it's something that I think is ridiculous, I want to know that, right? If it's something that doesn't really make sense, when we get beyond in the data it shows, for example, that men make better engineers or whatever it is.
And so you're talking about like, so first off, this is the conversation I wanted to have, because this is like before we were talking about explainability and trying to figure out like, well, is it possible for these algorithms to learn things that reflect the underlying mechanisms of the world that humans don't know about? And I think what you're suggesting, Rose, is like, can we kind of train these algorithms to do well and then try to figure out what it is they've learned? But to Payam's point, I think kind of what Alex is kind of hand waving as a solution is, he's pointing at the problem of putting blocks into putting blocks into the
Toy, whatever it is,
in the right shape. And so like so basically the specification issue is like, well, if all you specify is that it has to fit into a hole, then it's going to find all kinds of things that have nothing to do with the mechanisms that you're actually trying to use you're actually trying to generalize with, right? And so like you have to kind of, somewhere in that loss function, forget about a causal model. Maybe a causal model would solve it, but let's put that aside. Even maybe in just the loss function or somewhere in the training procedure, you can apply constraints to say, yeah, I'm not a topologist, but you can come up with some kind of topological constraint that says like, you have to maximize the amount of surface area of the shape being touched by the hole or something, or something like that. Right.
But then that goes against the whole machine learning approach, right? The whole point was you just specify what you want and the model will figure it out. Otherwise, you just go back to science and you do it the old-fashioned way. You think about what you want and you write down equations.
I think it's kind of the goal of the paper is like, if you just tell the machine learning what you want, without telling it, without giving it the right specifications, it won't generalize. It won't generalize what you want. And so like, I guess you want to kind of be minimal in telling it what you want. But I think there's a XKCD thing where he talks about like genetic or like every objection function should have put a negative 1 billion cost on murdering all humans or something like that. So it's like, yeah, you have to put on some, I think the constraints could be as simple as like, something like a cost function, but it's like, all right, well, we have to kind of be more specific than predictive accuracy in terms of loss function when it comes to specifying the constraints that we want to generalize with. And then, in that setting, say, all right, because the more we, so there's a trade-off, right? The more I specify, the better it'll generalize, but the less chance I have of it finding some kind of thing I didn't know about nature that it's going to,
I think there is one domain it works really well, right? That people are making a lot of progress, and that's like in physical modeling domain, like physics, let's say, right? I mean, you know conservation of energy, momentum, so those are as ground truths. So once you add those constraints, then people have been using neural networks to figure out the parts they didn't know how to do or they couldn't do fast enough. So then you get the best of both worlds. But of course, here, you know the ground truth. Like in reality, in all these people trying to Google doesn't know the ground truth, or nobody can ever know the ground truth in like social issues. So then it makes it really hard to actually do something about it. But yeah, I totally agree with Rose that you would want to sort of take the best of both worlds. I mean, humans are not infallible, so but that seems to be the best source of ground truth we have, right? I mean, how else are you going to judge your model, right?
Yeah, and I think like that, you know, the more I think about that Markov blanket example, the more it kind of is a good toy example, which is like, I need to specify that the variables that go into the model must be the Markov blanket, but no more than that. I don't even know the causal structure of the Markov blanket. But if I don't require that, then I'm going to overfit, or it's not going to, you know, like I could have a better model. So it's like getting the variables in the Markov blanket is one specification you can have that still allows you to get really good results without requiring you to additionally specify the causal structure of that model.
I don't know that you can ever get away from needing to eventually understand what pieces were combined to come up with the answer. Because I think what we find is that because there's just so much data drift in reality, that something that we believe to be fact for some reason today, we find out that there's actually something else behind it at some point in the future. And unless we can specify, I mean, I think the problem with this is that we come, especially when large amounts of data are involved, we come to believe that it is fact, as opposed to in this context, at this moment in time, not including these other pieces of data. I just don't see that we can ever do it without thinking about what elements were included in the decision making, so that we can then look further and try and understand, well, is there something else here going on that we're not seeing yet?
It depends on the stakes, like if it's approving people for loans or detecting cancer.
Yeah, that's a great point too, right? Like, I think it depends on what you're trying to do. And that's kind of where I think it's interesting to think about it in terms of just software development in general. Like when you're putting the way software used to be developed, and people would think about, okay, well, what are we trying to accomplish, and who are the users, and what's the specific use case, and all of that, and really engineer to solve a particular problem. Whereas I think we're believing there's a generalization there that really, I don't think you can get it as cheaply as you think you can. Like, things just don't generalize as well. And I think we're seeing that just even societally. Like, these things that we've believed are so true, they're so true for a certain set of people in a certain context. And then when we relook at it in 100 years, it's like, oh God, how could they have believed that?
Yeah, I think ML people, in general, probably understand all this. It's not that they discount all these issues. They're sitting on, let's say, Google sitting on all these terabytes of data. They want to make money out of it, or they want to do something, and you can't really go back to first principles. I mean, people are doing that, but that's not a scalable solution, right? And it's a very costly solution. They're just trying to get as much as they can out of the data without making any thinking about it, right? And yeah, I totally see that I mean, we see that it's causing lots of issues, but it also works in some ways, right? So
I honestly don't know what ML people believe, like, as honestly, like I like, you know, the last year or so of like squabbling on Twitter and, you know, and yeah, the machine learning subreddits. People find certain ideas to be controversial and politicized when certain ideas that I thought were just kind of like, oh yeah, this is clearly an issue. and so like I honestly I mean, I think sort of, I think, and it's hard because there's a lot of kind of specific voices out there who are just making a lot of noise, but I don't know what most people think. And I see a lot of extreme opinions online, and the internet tends to oversample extreme opinions, so to give you a distorted view of reality. So I have, for all I know, most of the machine learning community is, thinks that, predictive accuracy is like the third testament of the Bible. So
I think that's just it, right? A lot of it is just a tension between different worldviews, right? I mean, some people are pragmatic. I have this data, I want to get some results. You don't go and question the foundations of understanding. And then there are other people coming from the other extreme side, and they can't predict anything, but they can claim, oh yeah, we understand everything if we just connect these three circles together over and over again, and we write papers about it for decades, right? I mean, which is fine, but I mean, yeah, there's different goals, right? But I mean, I would say 90% of these causal SCM papers I open up, they show the same causal diagram with 4 circles, not more than that. And there is pages and pages of equations. That's not like, that doesn't give you a way forward, right? I mean, it's all interesting, but yeah, so I sort of understand both sides. I don't know what the right answer is, but I understand why both sides do what they do.
So coming up on time.
So one of the questions that we didn't address that I was curious to understand or get some insight on, maybe we can do this for next time. So in the entropy papers, my complaint that I kind of put into Slack, I still kind of stick to, which is all of these models that we come up with assume that the future is just a function of the past, right? So given some, if I know all the information in the world at some point t, I can basically make accurate predictions forevermore. And what's missing for me, and I've never seen it, is the idea of new information coming into the system, right? So some new emergent thing in the universe actually starts producing information that we haven't seen before, right? I guess the way that people say that they deal with that would say, well, it was always there, you just haven't seen it before. I guess that's true.
Give me 1 second.
Sorry. I guess where I'm going is, where is new information? Like, there's nothing anywhere about new information coming into the system. Everything is just, the future is just a function of the past. Sorry, what's that book?
This is a great book. I love it. It's like if you want a good introduction to information theory and all the misunderstandings about it, it's called Why Information Grows. And it goes in like very articulate way about exactly what you're talking about. How do you get new information?
Okay, can you, just offline send me the link and I'll definitely read it. Because this is the thing I struggle with, which is like everyone just makes this profound assumption that the future is just a function of the past, and I don't buy that. I mean, if that's the case, then why can't we have new information? Why can't new systems emerge? I don't understand. Why does everything have to be just the past rebaked in a slightly different way? Or am I misunderstanding the?
Well, it's a really interesting question. I mean, the way that Pearl deals with it says, look, the world is much more complex than we can ever possibly model. So we simply create a boundary and we allow for exogenous variables where we don't know, but there's some distribution. It's an unknown distribution, right?
Right.
So but then the question is, given this unknown distribution, we have this, endogenous model that we can talk about causally, but we have to acknowledge the existence of these exogenous variables. And furthermore, if those exogenous variables are correlated in particular ways, then you can't even predict what's going to happen on the inside, right?
But who thinks that we could predict indefinitely into the future? I think most people try to predict a little bit into the future, which is obviously doable.
Right. Well, all right. So then the other aspect is, what do you consider as part of your model and what do you not consider as part of your model? I mean, Stuart Kaufman makes this argument, says, look, basically contingency is a lot, like he talks about, like in some sense, like there's an irreducible amount of complexity in the sense that, what may have resulted in, a cell becoming, being able to reproduce may have been like some random cosmic ray that came and, changed this, flipped a bit of DNA, and suddenly now you have new possibilities you didn't have before, right?
Right. That's exactly what I'm trying to get at, Jeremy. Yeah. So some random event takes the causal pathway down some specific thing, and now all your models are wrong because we're in a new world, if you will. So is data drift just bad modeling, or is data drift partially caused by new information entering the system? I guess that's the question I'm trying to articulate. Is data drift intrinsic? Like, is it just
Data
something
drift
that
is intrinsic. I don't see any way you cannot have it.
I would agree?
Like if you have A and B today, tomorrow you're going to have A, B, B, A, right? Like it's just, you can't get around that.
It's interesting because there's like one case in deep learning where I've seen really good generalization, like real generalization, and in this graph neural networks, right? Like once you specify the relations between like two entities, even you can generalize to 100. Like if you look at the nearest neighbors, this is like abstract. I'm not trying to draw parallels to society, but I think there are ways that if you can understand the one-to-one relations between a couple of things, you could scale up to much bigger. You don't know what happens, but you can simulate it at least.
I think you can constrain things and put boundaries around it, but you never know when something is going to happen outside of your boundary that is going to have a huge impact. And that's fine, right? I think we can move forward with the models like that. But the problem as I see it is that we've lost the ability to try and just acknowledge that that is going to happen and that we need to constantly revisit it. We don't do that anymore. We have the model, we've proved it. Now that's a fact. Let's move forward from here and just we're going to cast aside everything that was on the edges, right? We've narrowed everything and we're going to continue to narrow. And these things that are happening out here are having dramatic impacts on the overall data generating process. And we insist on like, oh no, let's just ignore that. It's not an issue. It's over in the margins. It's like, it's not.
So
how can we go ahead, Jeremy, please?
I was just going to say, Robert, you had this really awesome article when I very first took your causal modeling course, where with George Soros and or maybe it was Warren Buffett, I forget now, but it was like irreducible complexity, or like the not irreducible complexity. It was a different word that you used, but it was this kind of notion of like inherent, like there's different kinds of uncertainty. Do you remember this? So
I remember writing something about Soros, but it was about falsifiability.
I saw that one about falsifiability as well, but this is more about, so maybe it was Buffett. I don't know. Maybe it was Buffett. Yeah,
I do remember writing something a while back on the different types of uncertainty.
Yes, and I think it was either Soros or Buffett was talking about, and we ended up having this whole conversation about black swans and all kinds of things, right?
Yeah, something about Knightian uncertainty. Oh man,
Knightian uncertainty. Yeah, exactly. Yes, but I couldn't even find it in the AltDeep modules anymore. I don't know if you cut the material or what, or maybe it was on the that Northeastern discussion.
I'll go look for it. I know I remember writing about it, but I don't remember.
Okay.
I don't remember where it was. Yeah, I remember I was in England when I wrote it. That's why it's coming back to me, but I don't remember where I published it. Sorry.
Anyway, so what do we want to do next time around? Do we want to look at the entropy stuff? Is that of interest to you, Robert? You seem to not be particularly kind of keen on it. Is the entropy stuff not particularly?
Like the entropy stuff as an objective function in reinforcement learning kind of idea?
Well, just essentially incorporating, so the claims of the first paper that you posted, Jeremy, my understanding was was that they were basically trying to make, well, how would you paraphrase it? I'm curious. How would you paraphrase the paper that you posted that we chatted about in Slack a few weeks back?
Oh, right. No, so that was so this guy Alex Gross Wisner Gross or something like that, right? And his paper on yeah, we had this whole long discussion about causal entropic forces as a physical relationship between maximum entry production and intelligence.
Right. Yeah.
And I also put the little link in there for the little video,
Which is very cool. Which is very cool. I do agree. Yeah.
Yeah. So yeah, so there's this whole kind of group of people who are like maximum entry production is like the one idea that like can explain everything, right? And there's actually a lot of mileage you can get out of it.
Is that worthy of further investigation, or is it just kind of an interesting sidebar, in your opinion?
I wish I had access to Alex Wisner Gross's software, right? I would like to be able to actually like see the software and actually get it to work, right?
I would agree that that would be a very useful thing to do, yes.
Because otherwise it's like this little demo and you're like, okay, but I want to peek underneath the box to see how it really works. I don't know. That's a good question. So I think it's probably worth spending a little bit of time on maximum entry production types of questions. Like at least getting enough background that we can at least, talk about the concepts in a way that, we can reason about them, right?
So this gets back to Rose's point about creating normative anchors, right? So we get a whole bunch of data and we come up with a conclusion, and then that conclusion is kind of carved into a stone tablet, and that forevermore, that shall be the conclusion. And we will, and I think this is a human cognitive bias, which is we will dispel entropy. That's why I kind of presented the paper that Rob suggested. So in Rob's paper, they're actually saying that we want to discard and remove the outliers, right? We want to essentially drive the system to normativity because that's when it's most predictable. And that's distinct from the first paper, the Grossman paper, wherever it was, which is they're saying that we should strive for entropy, right? We should try and not get trapped in these normative kind of belief systems and forever kind of challenge our beliefs and always kind of operate on the fringe. And I see these as being titanic forces pulling us in two very different directions. Does that make sense?
It does, actually.
Life, right?
Yeah.
Like, I just feel like you see this come up again and again, centralization, decentralization, right? Like, it's just, there's no right answer, right? We have to pursue all of them. And it's down to explore, exploit, right? Like exploit for some period of time, but recognize when you're no longer being.
I think that's a uniquely biological trait, right? Which is the recognition that the old belief system isn't working anymore, and we kind of need to essentially, we have some ability to determine that the model is broken and we need to move to a new model. So we have this cognitive bias built into biology, I would argue, that kind of has this flipping point. So rather than it being a continuous thing, it's kind of like, oh, it's not working anymore, we need a new one, right? And so we essentially throw away the stone tablet and create another one and use that for a while.
I think that we naturally also, as humans, I don't know, I think it's a very natural thing, and you see it with kids where they look at the thing that's different. Kids look for the outliers. Kids don't look for the normative. Kids look at, oh, what is this? I haven't seen it before. And I feel like that's what we're not doing. Like we're casting all that aside and focusing on, oh, well, this is what's happening in the majority of this. But I don't think that's how we learn. Like if you look at how most people learn, it's because they see something they don't understand. Like if you just keep seeing what you understand over and over again, it's like, yeah, the world is really easy, right? It's just like, okay, I got this. But it's when you don't understand something that you're like, oh, I need to learn more about this.
I guess where I'm trying to go with this is that can we imbue machine learning models with this ability to determine that the model is broken and that they should move back into an exploration mode? In other words, could we have a machine learning model or a machine learning pipeline that essentially incorporates this cognitive bias into the neural network itself? Or is this a human mediated process where we are the arbiters of when we need to change the model?
I mean, I think that's the explorer versus exploit, right? You need to constantly.
There are simple algorithms for that, right? Like UCB, upper confidence bound, right? I mean, it's really simple, but it's very intuitive, right? You explore places where you're most uncertain about, or it'll get you the most rewards, and you go between the two. And eventually there'll be less and less places where you're uncertain about, and you know exactly what you want.
So is that
beyond that,
information theory? Is that where to look for insight into that domain? Is that in information
I've
theory?
learned it in the context of like bandits, like reinforcement learning and bandits. But yeah, I'm sure you can look at it from information theoretic perspective too.
I was really just trying to lead us to what we should study next time. But let's just chat about it, I guess, in Slack and come up with an answer there.
A few suggestions. Like personally, I'm happy to read entropy stuff if people want to put together. If there's a reading list. Personally, I haven't been impressed with like the idea of using entropy in objective functions.
Okay.
Kind of make intuitive sense, but never really achieves better results. But that's just kind of what I've seen.
Fair enough. No, I've seen nothing, so you're doing better than me. But
I think on par with kind of what we discussed so far is some of these. So this is a woman at named Nana Min.
Oh, sure.
I think you collaborate with them.
Yeah, we just submitted a paper together to Prog.
Yeah, so she's her background's in like formal languages and verification. She's trying to kind of expand AI with that. She's trying to bring that intuition to AI. So she has a course here at Harvard that, and here's some of the reading lists.
Yeah,
the other thing is that.
Yeah.
Go ahead.
I suggested a number of these papers actually, like some of the early ones from like '94. The Ramonian Riva, and I kind of pushed her into the Perl. So now she's all into causality, right? That's great.
And so the other sort of, it's been Jeremy and Vincent and Jamie, we have been looking at a category theory course. I think we're doing it at different times, but it's, it might be useful just to kind of use this time if people are interested, because I think it was too early for Jeremy and maybe for.
All right, I'm trying to get my bedtime a little earlier so I can wake up for these things. They're super cool. It's much better than what I'm, doing it.
So what we've learned so far in that we can start it over. Like the category thing is cool because it's basically formalizing ideas of composability, right? So it's just like, all right, think about, say, causal Markov kernels. You can compose them into one causal model. Probabilistic programs, you can, if you're talking about explainability, then if you can assemble a model basically from like a toolbox of composable elements, then it becomes much more explainable. And so it kind of teaches you our idea. We've been looking at it because we were like, all right, why does everybody talk about category theory? Like it's really cool. And so like, let's just figure out what the reason is. And the reason is because it's like, it teaches you logic for reasoning logically about models and the data generating process. So that was less of a rating. It was more like a set of online courses, like online videos that we were watching. And we were actually kind of live watching it, so it kind of reduced the burden of. So it's kind of like watching it and then pausing it to talk and then watching.
Yeah, I've watched the first several. They're very interesting. I think that's a very useful thing for us to do. So I'm supportive of that. So
I am. Rose, what do you think?
I'm interested in category. I'm more interested in the category theory than the first one. The first one is a little bit too out there for me.
All right, cool. So I'll send information and we'll just use this time then. Jeremy, do you like that engineering course, or should we find something maybe that's more programming related?
I think this is probably a really good course, a first course to take, right? Kind of like it's kind of like the Book of Why kind of equivalent. You know, it gives you the conceptual foundation, and it gives you lots of examples. And I think that's really important, especially when you're learning category theory, because it's so abstract. Being able to ground these concepts in, oh, I can think of half a dozen different examples of this abstract idea is really, really critical. And so to be able to ground them in engineering examples is really great.
Yeah,
So I'm warming up to it. I really am. With the idea that we'll move beyond it eventually.
It's really like high level algebra, right? But like instead of like reasoning, whenever I saw category theory, like people would show me like, composability of functions. I'm like, oh, this is boring. I don't want to do this. But like, but like, they were doing recipes. Like one awesome example they had was talking about like commutativity and associative property, talking about like different recipes involving eggs, right? Like if you're making a custard, if you mix the egg and the milk and then the sugar, or you mix the egg, you mix the egg and sugar first and then add the milk, is not the same as mixing the milk and sugar and then adding the egg kind of stuff. And I was like, yes, that's true. It'll fuck it up if you do.
So mess things up.
So I really enjoyed some of the examples. So I'm interested in going further. It's
yeah. And in fact, I'm also going through those lectures on Monday nights. So if you guys are around or kind of want to talk about these ideas as well, then Marc-Antoine has actually got a little bit more background in category theory than I do, for sure. And so he's been summarizing the lectures. So we've so I think we're probably, even though I missed this week due to my sleeping habits, I'm still caught up to where you guys are.
So yeah, I mean, I've been looking for, I basically have more time now because my project is winding down. So I've been looking at trying to get into more of these reading groups. And the one I'm very interested in, based on the course that we just did, Robert, on probabilistic programming, is I'm trying to get up to speed with Omega. And so I read Zener's paper, the original paper on Omega. It's really cool, actually, his counterfactual mechanism using lazy evaluation. Yeah, that's very, very interesting. So that's one group that I'm kind of interested in following.
So you should join us on Monday, because we're going to be discussing that paper in the probabilistic programming and causality group.
Okay, I'd love to. So
that's Monday at 3 p.m. Eastern, so that's 12 p.m. your time.
Monday midday. Okay, great. I'm just saying I have more cycles. So if any of you are interested in doing a side project or something, I'm game. Like I really want to get my hands dirty and start kind of getting into some of the stuff that you've been teaching me, Robert. I really want to kind of get into that, and I don't know what quite the right path was. I was thinking about trying to use Julia, and I just don't know. Should I be focused on Pyro? Like, what's the right kind of on-ramp at this point in time to get into?
If you join the meeting on Monday, I'll introduce you to Alex Liu, who joins the call, and he works on gen.jl, which is a Julia language, which is where they focus a lot on making simulation-based inference practically useful.
That's exactly what I want to do. So that's perfect. Okay, great.
And I'd love to collaborate on that, because that's kind of a goal for me too. I mean, like, unfortunately, I don't think they have much in the way of documentation, but I can push them on that.
Maybe I can help. I don't know, but I'm just saying I do have cycles. I am genuinely interested in working on some interesting stuff with you guys, all of you, any of you. So if you have a project that you think would be relevant for us to work on, please let me know. So
I added everybody to the compositional thinking channel, and TWIML also have I'll create a thread for it in the All Deep forum. Yeah, so if you go to there's a link to a page on All Deep that has all the links for the courses. So
Great, I'll be there. Okay, so I'll definitely, and if you don't see me there on Monday, just message me because I probably can't find it or something. But yeah, I'll definitely be there. It's super interesting paper. So
So next week we'll just work through. I guess we'll just start over with the applied compositional thinking for engineers.
so should we pre-watch or watch it here?
You know, I guess it's up to you. I want it to be kind of low hurdle, so but you know, pre-watching would definitely help because it's, you know, math.
Mm-hmm.
Yeah.
Okay.
The slides are actually pretty good too. You
Yeah.
can read the slides and that's faster.
Cool. Okay. Sounds good. Let's do that. Rose, is that of interest to you?
I watched some of the first one and I wasn't so into it, but I'll look again. I'll look again. You guys you motivated me by being so enthusiastic. I started watching when you and Vince and
I have something for you. Just to motivate the question, I'm gonna send you a link to a video that's
Oh, the art and yes. Let's
I watched that.
I
I did watch that and liked that, but that which is why I went to look at the other one. And then when I was watching, I was like, oh God.
Which one? Wait, which one did you watch?
I watched she did compositional thinking with art, right?
Yeah.
Yes. Yeah. No, I really liked that. That was great.
Oh yeah, all right. So if you're motivated by the idea and the material sucks, then we can always just try a little bit and find new material.
How about it? I'll watch with you guys next week and I'll see. I just wasn't. I spent about 20 minutes and I was like, I'm not sure. But okay, I'll come next week and we'll see.
Okay, sounds like fun. All right, I'll see some of you on Monday then. Okay.
All right. Bye guys. Have a great weekend.
Yeah, you
Okay.
too.